All right, ladies and gentlemen, hello and welcome back once again to the longest running show in the world about data. It's called DM Radio. Yours truly, Eric Kavanagh here. And folks, I'm very excited to have two amazing people on the call today, two experts in the field of design, engineering, technology, all kinds of things these guys know. It's kind of amazing. We're going to have Sean Brehm. You may know him from our days talking about CrowdPoint Technologies, and Dr. Moshik Cohen is with us as well. And they have a new company called Luceon, and their company is focused on about the most important things that there are in the world, namely protecting us, protecting our country from harm. Folks, we live in very dangerous times, and I think that here in the States we can be lulled into a false sense of security because things are so nice here. We have this island fortress essentially. We have oceans in between us and most of our adversaries. But these days we have satellites and missiles, and we're trying to watch things. We're trying to see what's happening all around the world. And some of you may have watched the show I did with Dr. Cohen a couple weeks ago, which was really remarkable because he was instrumental in helping to defend against the largest missile attack in human history, arguably 200 and 300 ballistic missiles fired, in addition to drones and other things, fired at Israel, all shot down. So we're going to talk about today the sensing side of this equation. How do you keep tabs on countries like North Korea, like China, like Russia? Russia is the largest country in the world. It's massive. And I don't think many people fully appreciate the complexity and the challenge of trying to monitor and surveil the activity of people all around the world. We have the Iranians working on nuclear weapons. We have the North Koreans with nuclear weapons. The Chinese have nuclear weapons. The Russians have nuclear weapons. They move these things around. I remember when I was in high school, I had these books on the U.S. military, and I was fascinated by this hardware. And they showed how the Russians had all these mobile ICBMs. So they put them on trucks and they move them all around, so we wouldn't know where they are. Well, these days with satellite, you can see some of that stuff if you're looking in the right place. But if you're not
Yeah.
looking in the right place, you're not going to see anything. So, with that long introduction, let me welcome Sean Brehm, co-founder of Luceon. Thanks for being here, Sean, and thanks for caring about things that really matter to the world. Let's talk about surveillance. Let's talk about radar and some of the amazing things that Luceon has already put together. Give us your thoughts first of all on what is the gravity of the situation and what are you folks working on to solve for that?
Yeah, I think the biggest grab of the situation is when you think about this volume of sensor data, and we've talked about this over and over again on DM radio. I mean, like you're probably the preeminent guy on data. When there's so much data, you don't know what you don't know, and you don't know what questions to ask. Well, now you're entering into the world of everything could be a potential threat. And when you look at sensor data and you look at trying to define, what is friendly and what is foe, it's not so much that we can't detect something anymore. It's so much just how we can identify it. And when you
Hmm.
start getting into the realm of things moving at hyper velocity speeds, you've got to be able to identify what that pixel is telling you. Is it a bird? Is it something dangerous? Is it someone else flying a drone? And is that drone maybe interconnected to another thousand drones? So it's really about condensing space and time. And I think what you're going to hear from Moshik as he takes over and picks up the mantle for me here in a second is it's how do you condense space and time in a finite way to give you and surface fidelity.
Hmm. Well, and I think we're going to dive into signal processing. So, as you mentioned, I'm in the data world, and in the traditional data world, we have data warehouses. Now they have lake houses and things of this nature, where what you do is you persist the data, and then you apply a schema to that data, and then you analyze the persisted data. In signal processing, you're not persisting it first. I mean, you're processing as it's moving across the transom here. So you're in real time trying to assess what is happening here. And that's the key issue that we need to dive into. And that's kind of what Sean was alluding to. So, Dr. Cohen, I'll throw it over to you. And you're on mute just to be sure to take that. There you go. To throw over you, signal processing is the key, but it's all kinds of signals. And we're going to talk today about radar. Of course, satellites are also a source of sensors. You put sensors on satellites, you have data centers. There's a whole architecture here. But let's talk about the challenge of signal processing on massive amounts of data that has to be analyzed and understood in real time.
Yeah, good point, Eric. Thank you, Sean, for the introduction. It's really a good one. So, in the essence, sensors are means to capture the physical world and bring it to computers. Okay, so the world is huge, and you can look at thousands of kilometers, but at the end, you need to analyze the data in computers. So this is the sensors. Okay, and sensors are diverse. There's a lot of types of sensors. There's the cameras, which are quite similar to our eyes. There's the acoustical sensors, which are quite similar to our ears. There's the touch sensors, like our hands, legs, and body parts. We have the taste and smell sensor, which is more about chemistry. Okay, but there's a lot of sensors, and now there's active sensors. These are sensors that also transmit energy and process the reflections from the physical world. These are mostly radars, so they work on radio waves like you have in smartphones, which can propagate to very long distances. Okay, and there are also LiDAR sensor, which are based on lasers. Okay, so these are sensors. And when the sensors first receive the information, or more correctly, the data from the world, from the environment, it is mostly a stochastic data. It's not processed. You cannot understand anything of it. And now you need to start doing something in order to create some meaning out of this stochastic data.
Mm-hmm.
So the pipelines or the set of operations that one does from the actual creation of the data, which is mostly analog signals, so continuous signals, because the world is analog, it's
Right.
not digital.
That's right. I try to remind people of
we
that.
are
Everyone thinks
we
it's all
are
digital.
we
It's like,
are
no,
no,
even
we
digital is
are
analog to an extent, right?
yeah, if the sampling rate is high enough, so the world is analog equals digital, right? But in the essence, the world is analog, it's continuous. Okay, the operation is continuous. We are not discretized as a set of bits. However, in order to process information, to process the data, you need to sample it, so to convert it from the analog world to a digital representation. And from that point starts the signal processing. Okay, so the signal processing is about converting the data from a stochastic, hardware-centric, physical data to a representation of the environment.
Mm-hmm.
Okay, so and there is a lot of operations that happen in the signal processing pipeline, and each signal processing pipeline decides or determines the data quality, fidelity, and richness. And by the way, typically after the signal processing comes the AI. Okay, good. So the signal processing is sensor dependent because the target of signal processing is to process the physical data and convert it to a digital representation of the world.
Mm-hmm.
And since radar generates one type of data, camera generates completely other type of data, acoustics, and each sensor generates its own data. So each sensor modality requires a different and a designated signal processing pipeline.
Mm-hmm.
Make sense? And the signal processing pipeline is tightly coupled to the physics and to the hardware. Each physics required different pipelines, and each hardware required different pipelines.
Well, and
This is,
there's also the issue of intermittent signal, right? That this is my understanding with a lot of IoT, because we're in a sense we're talking about an IoT environment. You have lots of sensors. These are
Mhm,
devices that are
mhm.
connected by various
Yeah.
means, and the signals goes out sometimes. It doesn't, so you have to adjust for that too, right? It's not just that you're trying
Yes.
to analyze what's coming in. You have to recognize when you're not getting the signal you're supposed to get, and what
Mhm.
does that mean? Is it just temporary, or did the sensor go out?
Yeah.
Or whatever, all that stuff has to be accounted for as well, right?
Yeah, yeah, exactly. And this falls under the same big category that I defined, is how to correctly represent the environment.
Mm-hmm.
Okay. So part of the job of the signal processing pipeline is to also cancel the effect of interference,
Mm.
cancel the effect of false targets from that environment, cancel clutter signals from and noises from the hardware itself, from your hardware, in
Mm-hmm.
order to get the best and most accurate representation of the environment.
Mm-hmm. And all of that is built in. So we wanted to dive into the radar a bit, and you've explained that the radar, that technology that Luceon now has is so powerful, it can send signals. You were telling me the other day, you can actually bounce off of satellites and detect where satellites are. Is that right?
Mhm. Yeah. So so let's start with radar, because radar, I think, is by far the most interesting and potent sensor. And let me explain why. Okay. First of all, it has the longest detection range. Radio frequency wave can propagate for huge distances, and by that achieve very long detection range.
Mm.
Okay. Second reason, which is of course also fundamental, is the capability to measure all the 4 dimensions in the world. Our world is 4 dimensional. It's not 1, 2, or 3. It's 4 dimensional with 3 spatial dimensions. So the distance, okay, the horizontal angle, which is
Mm-hmm.
azimuth, the vertical angle, which is elevation, and then the velocity, okay, which is then, and the velocity is a different dimension, okay? So each object in the scene, in the environment, has its own velocity. And this is also a dimension, a critical dimension that only the radar can measure. Cameras cannot measure velocities. Acoustics cannot measure the velocities. They can estimate the velocity, but then it is not accurate enough for safety critical systems like defense and automotive safety systems. So
Mm-hmm.
radar is the only technology that has the longest range, can measure all 4 dimensions, and it is the most robust to weather, lighting, and environment conditions.
Mm.
Radar will work day and night, rain or fog, and
Right.
even when it covers in dust, snow, and other type of covers and problematic mediums.
Right.
Okay, if you look at camera, for example, if the camera is covered by dust, you will not see. Okay, so
Right.
it has the range, dimensionality, and robustness, and this
Mm-hmm.
is the reason why radar is the backbone sensor for every safety critical systems in the world.
Mm. Wow. Yeah, it's a big deal. And
Yeah, it's a big
again,
deal.
you have to, so we're talking about trying to protect, let's say, the United States, or let's just stay focused on Israel because that's the example that we have. Israel is not a huge country, so at least there's that. There's not a huge area to kind of
Yeah,
defend, whereas the United States is a very, very large country. It's not the biggest in the
yeah,
world. Russia's the biggest, but we're pretty big. And we have big, long coastlines. We have, all sorts of airspace issues. But the people who pay attention will recall a few years ago, a couple years ago, there was this balloon, this Chinese balloon that went
Yep.
all across America, slowly but surely, and apparently it circled around in Montana over where we have some ICBM sites. And you're like, what's going on here, folks? Like, what is this all about? Why are we not addressing this? And it went all the way across the country, and then we shot it down over the Atlantic Ocean, apparently. I mean, just real quick, we got about 2 minutes left in this segment. Sean, what was that all about?
I think it just highlights what Moshik just said, which is the sensor. We should have, it's just no longer the North America that we have to worry about. That launch of that satellite, you know, could have been, and I'm not going to delve into what actually happened, but it gives you a prime example where you look at sensor-based systems. If you're looking at the four dimensions of this, I mean, we certainly could have used data for trajectory optimization. We certainly could have looked at managing, being able to experience what kind of thermal were coming off of this, the signals, and we could have done structural integrity analysis on this. We could have done analysis on control systems ahead of time, and we could have solved all that problem long before it got here. And I think what even that slow moving balloon should surface to the average person watching this is, let's assume that everything I just talked about, there were certain agencies that were following that. And they were like, and there could have been very well a decision. Sometimes you let things come over just to get more information about it, right?
Right.
And sometimes it's, it could have been a great to do about nothing. And in other words, it could have been, we already made all those decisions at the standoff. We knew where it was going. We had an idea what we're going to do with it. And maybe there were some techniques to allow them to come in. Or it could be that it was a complete catastrophic failure. I'm going to go with the previous rather than the second. But at the end of the day, it's all about what we just talked about. Everything that Moshik just talked about is essentially that. It's about trajectory optimization. It's like using these sensors to figure out trajectory, identify whether that requires any kind of thermal management, any kind of an additional analysis and navigation control systems. But at the end of the day, that's all this is about. It's a simple process of managing those vectors. That's it.
Well, folks, don't touch that. We'll be right back. You're listening to DM Radio. All right, folks, back here on DM Radio, a fascinating show, talking to Dr. Moshik Cohen and Sean Michael Brehm, co-founders of Luceon, a company that has tremendous technology. And we're going to dive further into that in this next segment and try to understand the data and how you process that data. And Moshik, I'll throw it over to you. Before the call, I was just trying to get some crib notes here and ask you a few questions. And I thought there would be some material science here. I thought there would be some exotic manufacturing process in place, and you told me no, that you designed these things specifically to be able to be manufactured anywhere, like here in the United States. There's a big push to get manufacturing here in the United States these days, which I laud, quite frankly. I think we do want to be as independent as possible, especially when you're talking about systems like radar, defense systems, the technologies that are designed to protect us and our families. And that's some pretty important stuff. Again, I'll go back to this false sense of security that we have in the US because things are so nice here. We're far away from the battle lines, but that could end any moment now. Our Secretary of Defense, Pete Hegseth, commented that our carrier fleets can be wiped out in 20 minutes if bad guys want that to happen because of some of the capabilities that our adversaries have these days. I've got a long story of my history in that whole tall tale of terrible things that have been happening around the world. But let's get back into this radar capability that Luceon has, and in the ability also not just to detect, but to your point, to analyze and assess and make deterministic decisions about what it's seeing. So in the case where we had these attacks on Israel, 200 and 300 ballistic missiles, that's a whole lot of stuff for this for these systems to track. So can you kind of walk us through how you're able to track, many, many more things as they come? Because the idea is not just I'm stopping one missile. No, I'm stopping any number, n number, as we say in mathematics, to be able to handle that. So let's talk about how you built the deep learning system to be able to to convert all of this stochastic data into deterministic decisions. Go ahead.
Sure. So I want to stop on when we want to move forward from when we stop, right? On the signal processing,
Mm-hmm.
we explained that the radar is the backbone sensor for defense and safety critical systems. We now know that it transmits radio frequency wave like mobile phones, and we know that it is now measure all fourth dimension. So X, Y, Z, and velocity for each pixel on the scene. So, so the radar, so how it essentially works is that the radar creates some waveform, okay, in its hardware. It can be a pulsed waveform or a continuous waveform. And this depends on systems engineering and overall systems decision, by the way, including cost. Okay? This waveform is routed towards an antenna, and the antenna converts the wire-guided electrical signals to free space propagating waves. So the antenna converted from the wired information to free space propagating. Okay, and now you have waves that are propagating over the air. The waves are hitting the targets. They hit the targets, whether there are missiles, airplanes, satellites, and even human vehicles and drones. And then they reflect. There are reflections. Whenever the wave hits a target, a portion of the energy is being reflected towards the radar itself, and these reflections are processed, okay, via the signal processing. The first part of the signal processing called range processing. So by counting the time from the precise moment that the wave was transmitted to the time that the precise time that the reflected arrived back to the radar, by that, plus calculating the speed of light, which is the speed of propagation of radar wave, you can actually measure the range directly. Because range is c, velocity of light, times the time, the actual round trip time. Okay, so this is how you measure the range. And then after you mapped out the entire environment in the range domain called range profiles, now you process the velocity. The second part of the signal processing pipeline is velocity processing. So for each target, there is a direct measurement of the velocity. The velocity is measured, again, directly, without estimation, using the Doppler effect. Okay? And the Doppler effect means the change of phase versus the velocity, okay, as a result of the target's velocity. It's like an ambulance. When the ambulance is getting closer to you, the frequency of is getting higher, and when it gets away from you, the frequency goes lower. This is exactly the Doppler effect. So via the Doppler effect, the velocity of each target is measured. And after this range and Doppler processing, you get a map, a range Doppler map. Okay? And then there is the angular processing phase, okay, which calculates the angular location or the angular distribution of the target. So this is not only the range and velocity, now it's the height and the width. Okay? And after these four-dimensional processing, you have time varying cube with range Doppler azimuth elevation, range velocity, and two angles. And now things are getting more interesting, because this information also includes noise and non-desired signals called clutter and interference and adversaries that tries to block you
Mm-hmm.
You know, the Russians are very good in creating electronic countermeasure
Mm-hmm.
to block your GPS. You know that in the Ukraine war, the US JDAM bombs are just falling like rocks off the sky because the GPS jamming by the Russian.
Right.
So you need to also be aware of that and know how to handle it as a part of the signal processing. And this is way before we started discussing intelligent and deep learning. This is
Yep.
all hardcore part of the signal processing. So after forming the four-dimensional cube, you need to estimate the noise. This is very delicate. You need to find the precise mathematical distribution of the noise in the system. You need to know this is noise, and then you need to filter and subtract it from your system. After the noise estimation and subtraction, every signal that has a certain level of energy above the noise is considered as a true detection, okay? And by collecting and processing this detection, you get the actual word representation by the radar itself. So as you now understand, there is a huge data pipeline, which is not related to AI at all. It is rigorous mathematics and physical that converts this statistical signals to actual word representation. And this is what signal processing is all about. And this is the first phase that the data undergoes before, going forward to be semantically processed by deep neural networks.
Right.
And this is very much like what you've talked about when you've done your cybersecurity discussions. It's about removing the signal to noise ratio. That's the key. I mean, because there's just so much noise out there. It's not like we can immediately, in a time of peace, go, okay, everybody, stop using all your devices because we really just need to have the whole airwaves clear so we can see if something coming at us super fast.
That's funny.
Like that's not going to happen.
Right.
So what you have to understand is what Moshik just described is really a step-by-step process of where he was doing the data collection versus sensor, data integration and pre-processing. And the good news is you start immediately. And the reason why you start immediately on an everyday process is because now you can start taking what's happening in the world in a normal everyday perspective and start defining what we would call system rules. And when we do that, and when you and I have talked about this for a while, we're going to be incorporating some of the stuff we pulled out of CrowdPoint, which is our analytic tomography technology. And so we're going to basically do these things called like Hamiltonian formulations. And that's where we start defining the system data. And we start incorporating that system data. And then we start running what are called mean field calculations on it. That basically is nothing more to the listener, because they're probably like, oh my God, we thought Sean was crazy on his own, and now he's got Moshik, and Moshik was crazy on his own, and these two guys are going to just send us to the stratosphere in depth. Just to make it real simple, is what you want to do is once you take that, is you want to start simplifying the interactions. And you want to do that by basically, getting as much as you can to start predefining hard, soft, and absolute rules so that you can get into analysis optimization. So without that, without getting really effective analysis optimization through systems monitoring that Moshik was talking about, you can't get to predictive analysis. You can't optimize that. You can't start creating iterative improvements in the data, because every day as you run this, you want the system to get smarter and smarter and smarter. So what that means is you really got to perfect the data collection and noise identification. And that means really understanding your sensor deployment, really characterizing really what Moshik was talking about is noise characterization, right? And then when you start getting that done, now you can start getting into signal and noise modeling. And signal modeling is basically creating expected signal modeling. And we do that through a process called analytic tomography, which incorporates the known parameters that we've seen, or what we would call essentially the historical data on a day-to-day. This is what it looks like when I'm looking out from Hawaii, or I'm looking out from California, or I'm looking out from Florida. Then you start noise modeling this. You model the noise characteristics identified in the data. And that model helps us understand how the noise interacts with the signal, and it provides us the ability and a baseline for developing strategies. And once you're there, now you can start getting into that filtration and enhancement techniques. Now you can start designing filters, you can start enhancing signals. And then once you get to enhancing signals, you can integrate that with iterative optimization models where you're constantly learning, constantly redefining soft and hard rules. And you're really getting into this point where you can, when you start using analytic tomography, you can actually start doing signal to noise ratio evaluations over and over to get to a quality assurance mechanism. And then that helps you really to get into a more efficient remote sensing. So, the summary of what Moshik kind of talked about is that you want to address the signal noise program, signal noise problem. And the way to do that is augmenting it with kind of some of the advanced analytics like analytic tomography that we built in CrowdPoint, that we're going to be augmenting this kind of capabilities really to make these sensors smarter. Moshik, did I miss anything?
No, thank you, Sean. I think that you just provide a perfect opening to the more advanced part, which is the semantics. Okay, because everything that we talked until now is how to create a four-dimensional representation of the world. We know it's complex, it has the velocities, the spatial dimensions, and there's a lot of noise, which is statistic, hardware related, but also interference and adversaries. So after creating this 4D processing plus noise filtering, now the environment is represented by the sensor. Okay. However, now start the problem. Okay. We talked about a nearly idea scenario, but each system has its own limitations. And the biggest problem in radars is the resolution. Okay. Radar again stands for radio detection and ranging, and radar has a huge fundamental resolution problem, and it's directly related to the frequency and wavelengths.
Interesting.
Okay, let me give you a numerical example.
Yeah, let's pick this up after the break, folks. We got a break coming up here. We're talking to Sean Brehm and Dr. Moshik Cohen of Luceon Technologies. I think the company name is Luceon, I believe is correct.
Yes.
And we're talking about being able to monitor and surveil large parts of the world to understand what's coming. Is there a threat? Is there not a threat? If there is a threat, what is the threat? What's the nature of the threat? How serious is the threat? How many resources do we need to deploy to address this threat? These are the kinds of things that Luceon is able to do. It is proven technology. This is not hypothetical. It's worked. And we'll pick this up after the break, folks. Don't touch that dial. You're listening to DM Radio. All right, folks, back here on DM Radio with Dr. Moshik Cohen and Sean Brehm of Luceon. They are working very hard to protect us from the bad guys, folks. And there's some amazing technology. I was saying in the break there that I've been studying Apache Spark, which is the foundation of Databricks, a company that's now worth something like $40 billion. Yeah. And Ali Ghodsi founded that. I remember learning about it years ago. And they use a directed acyclic graph as a means for federating compute, for understanding what needs to be done, what can be parallelized, what cannot be parallelized, and to parallelize whatever can. So you can just basically roll out, basically spin up additional clusters, whatever you have to do. So I'll just throw it quickly over to Sean. You mentioned you've been using Apache Kafka and Apache Spark for years, right?
Yeah, for years. I mean, and it's critical we've been using it for our mean field Hamiltonians, because essentially once you build a just-in-time compiler that can handle speak that language and you can bring it in, it really helps you with your data collection. And then remember, we're talking about noise assessment from a radar threat, but noise assessment is important in cybersecurity. It's important for social media and analytics. And so what you want to be able to do is that technology has been around a while to help us go from collection and noise assessment to mean field formulations to signal processing, all the way down to resolution. So it's a great technology, and Databricks is a great company. Think about what we're going to talk about today is a new kind of Databricks where your sensor data, instead of being stored in the way Databricks stores it, but you store it in a distributed quantum ledger database. And all of a sudden,
Right.
you've got this a polymorphic atomic date time group stamped ledger that's got data associated with it, which is going to be all componentized or a part of leveraging Spark and Kafka like that.
Wow. And that gets us to the resolution issue here. And Dr.
100%.
Cohen, that's where Luceon really has excelled because if I recall correctly, traditional radar has the capacity that each pixel is like 100 meters or something, whereas
Yeah.
here you've got it down to, was it a centimeter or something like that? So you can tell the difference between a bird and a drone, right? And that's the point, is being able to ascertain what is this thing that I see on my radar, and what should I do about it? But explain how that happens. Go ahead.
Exactly. So this is the biggest problem of radars, and I think the biggest problem in defense tech at all, because radar is resolution limited. Like any other physical system, radar is resolution limited. And the resolution is directly related to the wavelength. Okay, what is the
Oh, right.
size
Right.
of the wave of a radar?
Right.
So all of us are used to optics because we have eyes. Eyes is the main sensor for human beings, for animals, for living creatures. And eyes work at optical frequencies that are most sensitive in the green wavelength, and the wavelength in green is 532 nanometers. So nano is 1 divided by billion. Okay, and this is the optical wavelength. However, the radar wavelength can be meters and tens of meters, and even more. So if people used to seeing objects in a highly detailed level of information, in most of in the radars, it's like blurbs, like that, because of the very low resolution.
Mm-hmm.
And this was okay when you talked about, the threats of the past, which means low count of threats with quite predicted routes, like ballistic missiles, maybe even airplanes, helicopters. So you have high flying metallic threats, which typically don't arrive in quantities of more than few tenths. Let's call it like that. And the distances between them are quite large, in the few meters, maybe a few tens of meters between the targets. So conventional radars can take care of that. Okay, and this is how the air defense sensors are built today. They have the typical pixel size of 100 meters. So it means that everything that, and there are some tricks to have sub-pixel detection, but in the essence, it is very difficult for today air defense sensors and today long-range physical surveillance systems to detect and understand information that has sizes of few meters and of course few centimeters, because of the very low resolution. And however, if you look at the threats of today, which are, for example, drones and UAVs, these are targets that are becoming smaller and smaller. And I recall now what Sean said, the birds, and they also fly low. Okay, they fly low, close to the ground, and as I said, everything which flies below 100 meters today is considered to be on the ground.
Yeah, right.
Okay, so you have then low flying targets that are filtered immediately by all current air defense radars. And as an example, I can give the the Houthis, the Iranian attack on Saudi Arabia oil facilities. These were done by drones, and these facilities were protected by US air defense systems, which didn't even activate the alarm.
Wow.
Okay? And in a split of few seconds, 50% of the production rate capabilities of the Saudi Arabia oil cut.
Wow.
And, market crumbled and oil prices destabilized. And all of this because the inability of current radars to detect these new type of targets. Not long ago, a UAV that was launched by Hezbollah traveled in the skies of Israel for 3 hours and hit directly in the home of the Israeli prime minister.
Wow.
Okay, it was flying for 3 hours and directly hit the home of the Israeli prime minister. So this is how dangerous these new threats are. And as we can intercept that from a mechanical perspective, and even with laser weapons and other soft interception techniques, we currently cannot detect them. These are the current technologies are blind to that threat. This is because the radar resolution limitation.
Right.
Okay,
Right.
now, if you want to increase the resolution of a radar, you can either increase its size, so it will be much, much bigger than the wavelength, or you need to create a radically disruptive breakthrough. And we at Luceon chose that part, to radically disrupt the way radar is working to create a highly improved resolution, which is in the centimeter scale instead of the 100-meter scale.
Right. Well, because you can use all kinds, right? I mean, there's linear frequency modulated chirps, phase coded pulses, continuous wave, for example. So you can think about how bats survive in these caves, right? They're using what is essentially radar to emit sounds that bounce off the walls, and they're able to not run into each other and do all kind of stuff. And it's like, wow, that's pretty cool. And that's kind of what we're talking about here, right? Is being able to, we got our last break coming up here in just about 60 seconds. So I'm just going to try to encapsulate a lot of this, and then we'll go into the last segment in just a moment.
Okay, so let me close and
Okay, 60
and
seconds. Go ahead.
make and rephrase that, because there are radars today, right? Macom does radars. Israeli primes make radars. However, it is diffraction limited in resolution. Okay, we are the only entity in the world that was able to break this diffraction limitation and create a centimeter level radar pixel. Okay,
Wow.
and by that we have a physical computer vision and understanding of the world.
That's crazy. We'll get into that in the final segment here, folks. And I guarantee we'll be hearing more from these gentlemen for lots of different reasons. Number one, it's fascinating, but two, it's so important. And a lot of times innovations occur just in time. And there are various theories for why that happens. I have my own theories personally as to why that happens, and I think Sean and I are on the same page there, and Dr. Cohen as well. But folks, don't touch it. We'll be right back. Podcast bonus segment is coming up. All right, folks, back here on DM Radio podcast bonus segment, talking to Dr. Moshik Cohen and Sean Michael Brehm. And Dr. Cohen, this is huge. I mean, the fact that you have solved for this one massive Achilles heel in the architecture and the engineering around radar, that's the key, because now you can get down to a centimeter, so you can tell from 200 miles away whether it's a drone or a bird. Is that right?
Yeah, it's right. And in general, the sub-diffraction resolution, super resolution techniques can work for any type of sensors. But if you go for safety critical systems, the radar is the most important sensor. So we chose radar, and now we were able to improve the resolution to a point that it can enable computer vision in 4 different dimensions, all day, all night, all weather, and nearly in every environment condition.
Wow.
Okay?
And
And
the part I get excited about is what Moshik mentioned. And what Moshik mentioned that probably went over most of the listeners is getting to the point that we can achieve sub-pixel detection. And that's where, you know, taking the concepts that we've been talking about with mean field Hamiltonians, because now you can actually apply what people are using every day when they go get an MRI. You can basically, you can apply this analytic tomography into tomographic reconstruction. You can essentially use analytic tomography to reconstruct the image or signal from the sensor data. And you can create a detailed model around it. And then you can, that gets you to the point where you start getting to enhanced resolution modeling. And once you start getting to enhanced resolution modeling, now you're getting into the cold concept of using what is called this Hamiltonian formation, which is defining how pixel values interact with at the finer scale. And once you're there, you get to this noise and signal decoupling, and you're now at sub-pixel estimation and refinement. That's what. That's why this is so exciting, because it allows us to not, you know, identify bang, but we'll be able to start identifying. And bang in a hypervelocity missile is essentially bang, because it's loosed and you've got millisecond response. So the whole key is you got to start building systems that's less, you know, left of launch, way left of bang. Does that make sense?
No, and just to explain to folks, just so people can kind of map this to their real world lives, think about apps like Shazam, where you're listening to the radio and you launch your app and it tells you what the song is because it's got a digital signature. It's something similar to, it's like pattern recognition. So there's an app I use called Picture This because I love plants. I'm a big closet horticulturalist, and I go around the yard and I take pictures of the plants, and it's like, oh, this is a black oak tree. That's cool. Oh, this is a vine. This is poison ivy. Don't touch that, right? This is the kind of thing we're talking about, but being able to do that with signal processing at a global scale, hundreds of miles away, even up into the stratosphere, even into outer space, for crying out loud. And what Sean is talking about is being able to put models in place then that are constantly monitoring. You can't just, monitor on Mondays, Wednesdays, and Fridays. You got to do it all the time. And so, there's a whole lot of, I'm sure, load balancing and all sorts of work that's done on the engineering side to keep these clusters rolling and keep them operational. Because the point is, Moshe, bang can happen anytime, anywhere, right?
Yeah, good point, guys. So I wanna just dwell one level down in the resolution area.
Yeah.
This is the key for nearly everything, from sensing to situational awareness and deep learning. Okay, if you go to the books, the scientific books, every system is resolution limited. Okay, every system is resolution limited in a hard-coded limit that's called Abbe diffraction limit. Okay, the diffraction limit sets the resolution bound to every sensing and measurement system. So far, the resolution limit, the size of the finest resolution a system can achieve, is dictated by the wavelength and its size. So the smaller the wavelengths, okay, the better the resolution.
I see.
This is why cameras typically have better resolution than the radar. And the bigger the system, the better the resolution.
Yep.
Okay? And now, if you look at any sensing and measurement system in the world today, specifically in the mobile world, in the real-time world, all systems are resolution limited by the diffraction limit. Okay? So Luceon is the first player in the world that was able to break this fundamental diffraction limit and achieve sub-diffraction imaging and sensing in all 4 dimensions.
Wow.
A very simple way to explain this for the listeners, because this is deep and this is deeper than we would normally go. But when you take what Moshik is saying, just on the collection and assessment side, and then you start augmenting it with a kind of analytics, how many of you? What's one of the biggest? Let me make this real simple. How many people are getting fooled by deep fake videos right now?
Right, right.
Right?
Lots
Okay.
of people.
So tomography, analytic tomography, significantly enhances resolution by utilizing data from multiple sets in the past, right? And you're able to create these advanced algorithms from hard, soft, absolute rules taken from this mean field Hamiltonian collection approach, and we can this is the as Clausewitz would say, der Schwerpunkt. We can reconstruct high quality image libraries.
Mm-hmm.
In other words,
You can see around corners.
yeah,
Yeah.
Right? I mean, that's kind of what we're talking about. So you sense a pattern, and you're able to then. I alluded to this early in the call about how IoT data can be intermittent. So you can lose signal for a second. Maybe it's
Mhm.
because a processor fried. Maybe it's because a cluster went down. Who knows? Things happen. The sensors break, and so you got to be able to work around that. And that's what you're talking about now. Is that when you have this full view of the world and you understand the richness of the textures of things, velocities, all you have these models to understand what's happening, then even if you don't have that one piece of data right now, you can reconstruct what it would have been,
you can
right?
reconstruct a high quality image, because what's more important in this kind of threat is you don't care what right looks like, you care what wrong looks like instantly.
Interesting. How
Mhm.
interesting. You don't care what
Yeah.
right looks like, you care what wrong looks like. You're managing the exceptions. I mean, that's what you're doing, is you're managing the exceptions, right?
Yeah.
Yeah, yeah. However, we need to be precise here because adversaries are very intelligent, and they can create, the bad looks like the good.
It's true.
Okay.
Wow.
So I wouldn't follow simple and binary rules, but I would go for more AI driven. But this is again semantics. I want to take us to a very simple example.
We got one
How we
minute, so
can,
bang
excuse
it out.
me,
You got 1 minute left. Go ahead.
1 minute. How do we detect or differentiate between a bird and a drone? Okay, a bird has its center of mass and it has wings.
Mm-hmm.
Okay, and the wings are moving in a separate velocity than the center of mass. A drone doesn't have it; it has rotors.
Mm-hmm.
Okay, and now camera cannot detect a drone from far distance at all. So let's stay with the radar. If you have even a 10-meter size pixel, all of the drone is a single pixel, and the bird is a single pixel. But if you have the centimeter level pixel, you can say, okay, these are the wings. Okay, and these are rotors. Okay, so this sub-centimeter imaging can enable classification from long range, even without AI, even with
Wow.
simple ruling. And this is the power of super resolution imaging.
Wow. This is great stuff. Well, folks, you're going to be hearing a lot more out of Luceon in the near future. Sean, Michael Brehm, and Moshik Cohen are both on LinkedIn. Look them up there. Dr. Cohen gave a keynote at Mar-a-Lago a couple weeks ago on some of these topics. And so they're working very hard, folks. And I cannot wait to talk to them next time, but our time is done. And
Yeah.
wow, send me an email, info@dmradio.biz. We'll talk to you next time. You've been listening to DM Radio.